Welcome to RISE Learning Machines seminars. I am Olof Mogren, and I'm a machine learning researcher at RISE, applying machine learning on environmental problems. RISE is Sweden's public research institute, and this is our open weekly seminar on AI and machine learning. This particular seminar is organized in collaboration with Climate AI Nordics. The meeting will be recorded. Let us know if you want to be removed from this recording prior to us publishing it on YouTube. And on YouTube, you can find an amazing collection of great talks that we've had through the years. Today, I have the honor to introduce Sherry Wang, who is assistant professor at MIT. Sherry obtained her PhD in 2021 in computational and mathematical engineering from Stanford University, supervised by David Lobel, and working in collaboration with the Center on Food Security and the Environment, and the Sustainable AI Lab. Sherry was then a postdoc with Solomon Xiang and the Global Policy Lab at UC Berkeley, and we're very glad to have her here today to talk about the topic today, reliable conclusions from remote sensing maps. And with this said, I will stop my screen sharing and hand over the word to you, Sherry.
Great, thank you so much for having me, and thank you for the introduction. Should I expect questions throughout this talk, or should we leave all questions to the end?
It's mostly up to you.
Okay.
If you're okay with being interrupted, I think that gives a nice interactive feel to the seminar.
Yeah, that sounds good. If anyone has any questions or wants to make any comments, feel free to interject or raise your hand. Great. So today I'll be talking about drawing reliable conclusions from remote sensing maps. And before I go into that more technical portion of the talk, I just want to give some background on the work that my group does and some of the exciting data that we work with. So I guess not everyone may work with satellite imagery. So I'd like to start by showing a video of the Landsat satellite. And this is the kind of data that we now have access to where Landsat flies over orbits our planet, and as it flies over, it's continuously taking pictures. So over the course of about every 8 days, it will image the entire Earth. So the state of the art of remote sensing or satellite imaging has really advanced in the last couple decades, and we can see that when we track both the spatial resolution progress as well as the revisit time. So Landsat 8, as I mentioned, has 8-day revisit and 30-meter resolution. Then with the Sentinel-2 constellation, we have now 10-meter resolution with 5-day revisit. And with the Planet Doves, which are a commercial constellation, we now get 4-meter resolution with daily revisit. So we're really excited about what this means for what we can monitor on our planet. We also have, in addition to ever advancing spatial and temporal resolution, we also have more modalities. So here is a bunch of different sensors, both currently up in space and planned. And there's a lot of names here that, are a lot of acronyms, but basically there's not only optical satellite imagery, but also active radar, there's LiDAR, as well as hyperspectral imaging and other modalities. And what we can see using satellite imagery now are many things, but here's a time lapse to give you a maybe intuitive sense of what we can see. So you can see rivers changing over time, you can see urban development, you can see deforestation and more. And the new modalities that we have also open up doors for new types of things we can sense, such as, for example, LiDAR. People use it to estimate above ground biomass. And with radar, you can also see subsidence, which means the land sinking due to for example, groundwater extraction or just urban development. And one way I like to think about, what can we use satellite imagery to monitor is by referring to the Sustainable Development Goals, which were developed in 2015 to be reached. The goal is to reach them by 2030. Of course, they're very large and ambitious goals, such as no poverty, zero hunger, climate action, and so on. And what's unique about the SDGs compared to the Millennium Development Goals, which were their predecessor, is that they have 230 indicators that are concrete and trackable. So in order to make progress, we have to be able to measure things. So in addition to these large goals, each goal has kind of sub-targets. So here's an example of something that we don't have very good data for, but we might be able to fill this gap through remote sensing. So target 2.3 under SDG 2, which is zero hunger, is to double the productivity and incomes of small-scale food producers. And this map, which is from a few years ago now, but the situation hasn't changed that much, is showing where we have data on the income of small-scale food producers. So everywhere that's gray, we don't have data for. So it's very hard to, make progress when you don't know where we currently are and also how fast we're moving either toward or away from the goal. So this is, of course, understandable when you think about what it takes in order to get this kind of data. So usually these indicators require surveys where people have to go and talk to households or do farm surveys. And that takes a lot of statistical capacity that not all countries have. They also, because of the just how many samples you're able to get, it's hard to draw conclusions at very high spatial resolutions, and it's hard to refresh this kind of data very often. So, you often only have annual data for many indicators if you have data at all. So, even for something like as important as GDP, we don't have GDP at the subnational level for most countries around the world. And if you don't have highly granular data in both space and time, it's hard to answer questions about why some policies or some technologies are successful and other ones are not. It's hard to understand the impact of climate change at a more granular level. Okay, so we're excited about satellite imagery because there's a lot of things we can see in satellite data, such as economic activity through night lights. You can see a lot of things about agriculture through optical remote sensing. You can also see flooding and other events. You can also, with very high resolution satellite imagery, potentially even see things like illegal fishing. And of course, we like this data because it's global in nature. Once the satellite is up there, which of course does cost quite a lot to send a satellite into space, but once it's up there, then the marginal cost of new acquisitions is low, unlike surveys where the marginal cost is still high. And then again, we're aiming for this really high temporal and spatial resolution. At the same time that we've seen this very rapid advance in Earth observation capabilities, which you can see on the left, there's a line here showing the 3-year moving average of the spatial resolution, as well as the number of satellite launches per year. At the same time that this has been happening, we've also seen, of course, this huge improvement in our ability to process image data and unstructured data in general, thanks to machine learning. So I think with this audience, I don't need to emphasize that point, but now we have the tools also to process and extract information from or knowledge from all of this new information that we have. Okay, so my group at MIT started 2 years ago, and I call it the Earth Intelligence Lab, or we call ourselves the Earth Intelligence Lab. And we view the main goal of our research as to go from where we currently are, where we have these coarse spatial resolution maps that are updated infrequently, to a world where we have high spatial and temporal resolution monitoring of various indicators so that we can develop more sustainably. And I like to divide our work into 3 main buckets. The first one is algorithmic development. So that includes machine learning in label scarce settings, because a lot of times we still, there's kind of this catch-22 where we obviously need labels in order to train our machine learning algorithms. But a lot of times we don't have those labels to start with. So advancing what we're able to map also through algorithmic advances is one of the things we're interested in. Other algorithmic advances include leveraging the unique characteristics of remote sensing data and creating benchmarks so that the machine learning community can test new algorithms on these global data sets. Second, once we have algorithms, or even honestly with very simple algorithms, a lot of the time we can create these large scale accurate maps with valid uncertainty quantification so that we can do subsequent analyses. And in order to make new data products, we also, one of the things we do is explore the use of novel data sources. So that can be on the label side, as well as on the kind of feature side. So what kinds of satellite modalities allow us to map which variables. And lastly, once we have data products, we're interested in assessing the impact of policies, technologies, and climate change on variables like, agricultural yields or what farmers are choosing to farm, and so on. So I guess let me give a few examples of some of our recent work and point out what kind of, or like what category they fall into. So this is a more algorithms focused work where we wanted to understand, do the current LLMs or vision language models, are they able to perform geospatial tasks? So if we ask ChatGPT to count, refugee tents in a satellite image, like will it be able to do that? Or do we still need to develop specialized algorithms in order to do that? So in order to answer this question, we basically developed a suite of evaluation tasks, which we call VLEO bench. And we found basically through evaluating a bunch of vision language models on these tasks that the strengths of these models are really, they really go back to their world knowledge. And so they're able to generate very good captions for images, and they're able to recognize landmarks from satellite or aerial images. But they're not very good at counting things like the number of buildings in an image, and they're also not very accurate at putting bounding boxes or figuring out, locating basically localization of where things exactly are in images. And this is, obviously a field that's developing extremely quickly. So this is from a year ago, and things have changed somewhat, but I think that some of these patterns actually remain. So we're hoping to do a refresh on this benchmark soon. Now on to developing actual data products. A couple of the maps we've made recently include creating the first ever crop type map of Thailand in 2022. And this was work published at AAAI last year. And the kind of key bottleneck for mapping crop types around the world is the lack of ground labels in most countries, especially smallholder systems, contrasting against industrial agriculture in places like the US, Europe, Australia, Brazil. So here our insight was, we have more and more roadside images, for example, Google Street View type imagery than ever before. Obviously, those cars drive along roads and have a lot of data in urban areas, but they also drive through agricultural regions. So can we extract at scale information about crop types from those rural images in order to supervise a second machine learning model that relates satellite time series to what's being grown on the ground? And it turns out, yes, we're able to do this at scale, and we did it for the first time in Thailand, showing that it's possible, mapping 4 of the main crops in Thailand that together cover 90% of Thailand's area. So we mapped rice, sugarcane, maize, and cassava. And this was done to over 90% accuracy. So quite an accurate map by really any standards. Okay, great. And then another example of a data set we created was global mapping of sugarcane at 10-meter resolution. And this was made possible by the insight that sugarcane is taller than other crops, and also not only taller, but taller for longer than other crops. So, maize, for example, is also a tall crop, but it has a much shorter growing season than sugarcane. So we used the JEDI instrument, which is a space-based LiDAR instrument on the International Space Station. And because JEDI is able to map vegetation height, and it was originally designed to map forest or tree canopy height, but we tested it to see if it could still distinguish between tall crops and short crops, and we found that it can. So using JEDI shots from around the world, we look at how basically if a particular location has a tall crop for a long period of time, then we believe that that location is growing sugarcane. So with this insight, we're able to make a global sugarcane map at 10-meter resolution. Also, this is the first time sugarcane's been mapped at such a high resolution. Okay, so are there any questions? Maybe I'll pause here for a bit, because next I will dive into the more technical portion of the talk where I explain not about making a map, but once we have a map, how we can draw reliable conclusions from it.
Did you mention what kind of satellite data did you use for the crop analysis?
Oh, for both the crop type map in Thailand and the global sugarcane map, we used Sentinel-2 to make it a wall-to-wall map.
Right.
So in the first case, the ground truth labels came from Street View, and in the second case, the ground truth labels came from JEDI.
Thanks.
Yeah.
I think Leif has a question as well.
Yes, I have a question, and this is probably an incredibly stupid question, but 10-meter resolution, that means you cannot detect anything smaller than a 10-meter square. So that will be 1 pixel on your map. Is that correctly understood?
Yes, that's what that means.
Okay. And again, being incredibly naive in satellite imagery, I would have thought that we could get a higher resolution now. But is that because we really can't, or is it just because it's too expensive?
So we can get higher resolution from Planet with very high temporal revisit as well. If you go to even higher resolution, those sensors, what you think of when you look at Google Maps, those satellites are tasked, which means that they're not always on. You have to pay that satellite company in order to take a picture in a region that you're interested in. The difference between that and Sentinel-2 and Landsat is that Landsat and Sentinel-2 are always on. So you get a reliable 5-day or 8-day revisit. So basically, the higher resolution you go, usually those satellites are tasked, with the exception of, I would say, Planet, which is that 4-meter daily revisit satellite. The kind of challenge of working with Planet data is that we have universities often have or sometimes have licenses, but it is still kind of up to researchers to download all of that data and process it, versus data like Sentinel-2 and Landsat are already available on platforms, cloud platforms like Earth Engine, where you don't have to download all the imagery yourself in order to, train a machine learning model to do that crop type classification.
Okay, so it's essentially a cost issue then. I mean, they could technically put a bigger lens on this, the one you're using, and you would get higher resolution, but it's a cost question then.
I guess I'm not that familiar with sensor design, or why for the next generation of Sentinel sensors we don't make them higher resolution, but yeah, I imagine there's technical challenges there.
Okay, thank you very much.
Yeah. Okay, great. So a lot of the work in my group is on making maps, but we want to make sure that once we spend all this time making maps, we want to make sure that they're actually useful for downstream analyses. So I think one typical workflow right now is one research team produces a remote sensing map, and then other researchers download it to use in a statistical analysis. And, we kind of have more and more remote sensing maps made by, labs from all over the world. And you can see that, for example, there's a catalog on Google Earth Engine called Awesome GEE Community Catalog. And it now has, I think, I saw the other day, it has over 4,000 data sets, in particular over about 600 image collections, as of last week. So there's really a lot of variables out there that different groups are mapping. Here's just one example from CSIN and Facebook, the high resolution settlement layer. And so I think there's a lot of people, a lot of economists and people working in policy who want to take these maps and be able to do these high resolution analyses that, when we make maps, we really dream of them being used for. And when I say statistical analysis, what I mean includes things like area estimation. So I made a crop type map. Now I want to know what's the total area of rice, in every district of Thailand, for example. That type of making that statistically unbiased and have confidence intervals that have the correct coverage. We have methods for that kind of area estimation. We've had them for decades now. I would call them post-stratified estimators. There's another type of statistical analysis, however, that we haven't tackled yet, which is using remote sensing maps in a regression. And so to give a little bit of background, or here's an example, you might want to know what is the effect of protected areas on deforestation. So in addition to making maps of deforestation, assessing their accuracy, having confusion matrices, and being able to say, oh, that pixel got deforested, if it wasn't supposed to, then you can send law enforcement there. We also want to use them in analyses like, okay, we made a protected area here. Did that actually effectively reduce deforestation in this area? And this is a real question that a lot of environmental economists are interested in. And so what often they would do is take, for example, a remote sensing map of deforestation and have it be the Y variable in a regression. And then the independent variables on the right-hand side here would be the treatment that they're interested in, which is whether that a particular pixel was inside of a protected area or not. And then there's a bunch of control variables, because of course you don't want to be comparing apples to oranges. There's lots of reasons a pixel might be deforested. You want to be comparing pixels that are otherwise, equal in as many ways as possible, except for the fact that one is in a protected area and one is not. So you have a bunch of control variables, you have intercepts, and then you run this regression, and then the interpretation, if the specification of this regression, can be interpreted in a causal way, then we would interpret the coefficient on protected area as the impact of making a protected area on likelihood of deforestation. Okay, so that's the kind of analysis that we want to make sure that we can use remote sensing maps for, because people increasingly, they want to use remote sensing data sets or remote sensing based maps for these kinds of analyses, but it's also, the lack of guarantees that they would get unbiased estimates out of an analysis with remotely sensed maps is stopping people from using these data sets in such a manner downstream. Okay, and people in the field of environment and economics and policy have already rung the alarm bell about using these satellite-based data sets for inference for a few years now. So these are both papers from 2023. The first one outlines the benefits and pitfalls of using satellite data for causal inference, and the second paper is called Remotely Incorrect: Accounting for Non-Classical Measurement Error in Satellite Data on Deforestation, and they look at deforestation, I think it's in Mexico, and how basically there's errors or at least disagreements among different data sets, and you draw different conclusions, and we need to figure out a way to debias the estimates. Okay, so the main problem here is that remote sensing based maps, like any product of a machine learning algorithm, those predictions are going to have errors, and maybe some amount of the error is classical, which is to say that the error in the measurement error, or the error in your predictions, is it could be independent from the other variables in your regression, or more likely, a lot of times they're not going to be independent. So in that case, they would be considered non-classical errors. And both types of errors would be problematic for this kind of regression-based analysis. And I'll go into that a little bit later. But here's an example of the kind of systematic errors that we see in remote sensing maps. So we know, for example, that deforestation maps will miss small scale logging. They also miss, other types of things, but missing small scale logging would cause us to underestimate the amount of deforestation in a systematic way. Yield maps, so crop yield maps, we know that they tend to overestimate low yield. And this is an example from the first paper here. You can see on the x-axis, the predicted crop yield, and then on the y-axis, the observed crop yield. So, I mean, this is in India, which is a smallholder agricultural system, quite heterogeneous landscape. It's not an easy task to map yield using remote sensing in these locations. You can see the R-squared isn't super high. And then there's this problem that basically at low yields, basically the model kind of flattens out and is not able to get the lowest yields down here. But this map also, I would say, the R-squared or the correlation here is not 0. So if we still wanted to proceed with using such a map to draw some downstream conclusions, how do we do that? And how do we know that the conclusions that we draw, aren't terribly influenced by the errors that exist in this map? Okay, so mathematically speaking, the problem is when we have not the perfect version of a variable measured. So in this case, let's say we don't have the ground truth X measured everywhere that we're interested in, but we do have a proxy for it, which we call X hat, which would be, in this case, the remote sensing map. The issue is when the error in our measurement X hat, it's not independent, or there's a non-zero covariance between the error in the map product and the error term in the regression. So in that case, then your estimate for beta, which is what you're interested in these types of analyses, beta will be biased. Okay. So there's been some recent work to remedy the situation and kind of enable use of these kinds of maps for analyses that many people are interested in without getting biased results out of it. And so I won't go through each of these, but basically 3 of the characteristics we may be interested in would be that, a method is easily generalizable to many statistical inference tasks, that it doesn't apply, it's not too tailored to any specific type of analysis. We would want also, of course, the estimate to be guaranteed to be unbiased, as well as for there to be confidence intervals, and for those confidence intervals to have a guaranteed coverage. So if you want a 95% confidence interval, and that's what you get from the algorithm, you want to know that actually the true parameter is going to lie in that confidence interval 95% of the time. So that's what I mean by correct coverage. And you can see basically, these different methods, they kind of address each of these ideal properties, or they meet each of these ideal properties kind of in different combinations, but there hasn't really been a method that really meets all of them very well. So that's why we kind of are motivated to develop a method which is actually related to the last method in this table. Okay. Any questions before I go on to what the method is? Okay, so the setting that we're interested in is when we actually have some ground truth data in addition to our map product. And the conditions on that ground truth data are that they have to be somehow randomly sampled. So it doesn't have to be a uniform random sample. It can be stratified random sampling, weighted random sampling, clustered random sampling, et cetera. But there does need to be a random sampling component to it. So in that case, let's say in this picture where we have a map of forest cover in the United States, and then we also have some number of ground truth points of forest cover at each pixel, or at the pixels where we have the ground truth data. So we have little n ground truth points, and we have big N points or pixels in the map product, and big N here is much, much bigger than little n. So that's the typical setting that we find ourselves in remote sensing. So two typical ways that people have, tried to estimate regression coefficients or just parameters using such data sets are to kind of just do an analysis with each of these. So if you have ground truth points, you just do an analysis with only ground truth points. And the nice thing about this, of course, is that if the ground truth is randomly sampled, then the conclusions that you draw are going to be unbiased. However, you are missing out on the fact that maps might exist of the thing that you're interested in, and so you're not gaining anything from potentially millions or billions of pixels in these remote sensing maps. So you don't you have a wider confidence interval than if you made use of these maps. The second thing that people often do is they just treat the map as if it were perfectly accurate. So they just ignore the errors in the map. And you get a very narrow confidence interval. You feel very confident in the thing that you're estimating, but you're not guaranteed for that estimate to be unbiased. So what we do instead is we propose to combine ground truth with the map product in a framework that we call prediction-powered inference. And as a result, you get something that's guaranteed to be unbiased and with a smaller confidence interval than what you would get from only using the ground truth points, because you also made use of the map product. And I mentioned this previously, if you're just interested in doing area estimation, you can use PPI, that will still work. You can also use what has been used in the remote sensing field for decades now, which is what we call the post-stratified estimator. Basically, for example, if you're interested in the area of rice in the US, you would just take a confusion matrix for the map, and that would allow you also to get an unbiased estimate of how much rice there is, even if there's errors in the map. Okay, so mathematically speaking, we have these two data sets. The ground truth one I call the calibration sample. And for the calibration sample, there's little n points. We observe, in this case, let's say we observe the true y. And if you're using a remote sensing map of y as well, then you also observe y hat, or the proxy for y, at the calibration points. You observe your independent variables x, and then any of those that are also have a remote sensing map. And then for the map sample, which is big N, much bigger than little n points from a map product, you don't observe the true values of y and x. You only observe their proxies, so the map products. And again, we're doing a regression, and what we're really interested in is getting unbiased estimates of coefficients on our independent variables, which we might interpret, for example, as a causal influence of x on y. And we also want confidence intervals for those coefficients that are valid.
Question.
Yes.
This assumes that you have a map product that gives you the target variable, or an estimate of the target variable.
Yes. Like we're talking about cases where people may want to use a deforestation map for y, or people might want to use, in the agricultural realm, we've done analyses where we look at what's the effect of tillage, which is basically when you till the soil. That's when you stir up the soil before you plant seeds in it. What's the effect of tilling the soil versus not tilling the soil on crop yields? Because people are trying to, encourage adoption of low till, which is like leaving the soil in place, so that we reduce soil erosion and reduce carbon loss from the soil. So, you might do a regression where tillage status, which is tilled or not tilled, is also something that we remotely sense. And that's something that we've actually done before. So X might also be remotely sensed. And then Y, which is a yield map, could also be remotely sensed. So this kind of analysis you could do, at the country scale, but you might only have a calibration set, at a pretty small number of points around the country. That's kind of the setting that we're thinking of. Yes. Okay, so mathematically speaking, the classical approach where you only use the calibration or ground truth sample is, we're going to call the estimator beta hat calibration. So that's just the estimator that we get from this solving this least squares equation, where again, the samples that you're minimizing this squared residual over are the small n points in the calibration data set, and then you're using the true ground truth values in order to find beta hat calibration. So this estimator is unbiased, but again, it has a large variance because n is small. Now, what we call the naive approach is treating map predictions as truth. So just ignoring the errors in there. And we call the naive estimator gamma hat map. And this is using the big endpoints from the map, but we are using proxies for y and x, not the true values of y and x, because we don't have them everywhere on the map. Okay, and the reason that we call this estimator gamma instead of beta is because there's no guarantee because of map error that it's unbiased. So in general, it will be biased. It will have low variance, which we like because big N is very big, but it's biased, and it will even in the case where big N goes to infinity, the gamma hat map will converge to some quantity that we call gamma instead of beta. So that's why we use the notation gamma here, just to emphasize that, even in the large sample limit, it's not guaranteed to converge to the true value beta.
So I have a question there. So
Yes.
why I here? Can you give an example what that is? Is it a true false, or is it a nominal value, or is it actually a continuous value?
Oh, it can be any of the above. It can be deforestation, like Y can be deforestation status. So it could be binary, it could be, or like a value from 0 to 1, percent forest cover, or it could be just, we just deem this pixel to be deforested or not deforested. It could be yields, which would be, numbers above greater than or equal to 0.
Okay.
Yeah, it could be anything.
All right, thank you.
Yeah. Okay, so when we run an experiment here, we see the behavior that we described in the previous slide. So let me describe the actual setup here. So here we are regressing housing price. So this is in the United States. We're regressing housing price on independent variables, night lights, road density, and income. Okay, this is not meant to be an actual causal inference regression that somebody would run, because I think that this specification, you can't argue that this is causal. This is just a toy example for us to illustrate the method. So this is what Y and X are. And then for X hat, we have satellite based, which is to say using daytime high resolution satellite imagery. We then make predictions of night lights and road density. And I don't know if you guys are familiar with Esther Rolfe and others' paper on mosaics, but that's the paper that these data sets come from. Anyway, so the only thing you need to really remember here is that we're doing a regression, of one variable on 3 other variables, and then 2 of those X variables are remotely censored. There's some kind of proxy for them. So the classical approach, which is where we only use a few locations where we have ground truth data, basically the true coefficient is this dashed line here. This is the true coefficient of night light in this regression. It's around 0.12. So the classical approach using only ground truth, if you run this regression multiple times with bootstrapped samples of your ground truth, you get a very wide spread in what you estimate that coefficient to be, but your estimates are unbiased. So they're centered on the true coefficient. Whereas if you have the naive approach, which is where you assume the map is just error-free, you get something centered closer to, let's say, 0.15, which is biased. So it's not converging to the true coefficient, but the spread is much narrower. So this is the behavior that I described in the previous slide. And so our solution is to combine the ground truth data with the map product to kind of get the best of both worlds, something that's unbiased with a narrower confidence interval than the using only ground truth data. So the idea is to use the calibration set to debias the map-based estimate. So another name that we use to refer to this method is predict, then debias. And this is a method that, or like a procedure that originated in the measurement error literature, dating back to Chen and Chen in 2000. And then because of this proliferation of machine learning generated predictions and people wanting to use that kind of data in downstream statistical inference. So this applies not only to remote sensing, but also to, other kinds of machine learning data sets. It's been more recently studied, starting in 2019 in all of these papers as well. Okay, so what is this estimator that we introduce, or we kind of, I would say, piece together from the literature? It's basically computing gamma hat on the calibration set. So recall we had this gamma hat on the map sample. Now we compute a gamma hat only on the calibration sample. So that means using the proxies for y hat and x hat, but only on the points 1 through little n, where we also have ground truth data. Okay, and then our estimate for beta with our method, which we call beta hat PPI, that's going to be the map only estimate, which again, we know to be biased, plus a correction term. And that correction term is the difference between beta hat on the calibration set and gamma hat on the calibration set. And we know that this is unbiased because, or let's say consistent, which means that, as little n and big N go to infinity, we know that beta hat PPI converges to the true beta because each of these three terms will converge to gamma, beta, and gamma respectively. And so the gamma terms will cancel out, and then beta hat PPI will converge to beta. And then, so how do we then think about the variance of beta hat PPI? Well, the variance of beta hat PPI under an independence assumption, which is to say that the gamma hat map term is independent from this bias correction term, then it decomposes into two variances. The first one is just the variance of the map-based estimator, which we know is small because big N is very large, and the variance of the bias correction term. And basically, the more accurate your maps are, or the more accurate your machine learning predictions are, the smaller the variance of this difference. The closer gamma hat calibration will be to beta hat calibration. All right. So when we actually run the predict then debias estimator on the same regression task, we see indeed it is unbiased and it has a smaller spread than the classical approach. Okay, so I'll talk about a couple of more technical things, and then I'll go into a bunch of remote sensing experiments that we do. So I won't spend too much time on this, but basically we noticed that if the map is very inaccurate, so if your machine learning algorithm, if your predictions are really bad, then you could have a case where beta hat PPI is actually has a higher variance than beta hat calibration, which is to say using only ground truth points. Like adding the map to your analysis is giving you a higher variance estimator than only using the ground truth points. So in order to prevent this from happening, we introduce a tuning matrix omega. And basically we just multiply the gamma terms in the equation for beta hat PPI by this omega matrix. And we know what the optimal form of this matrix is. In reality, they have to be basically omega has to be estimated from our data set. But if you use omega, the optimal version of omega, then the variance of your PPI estimator is guaranteed to be no greater than the variance of your ground truth only estimator. Okay, and this is explained more in our paper, which is on arXiv and currently under review. Okay, so I won't go into this really either, but I just wanted to note that the way we construct confidence intervals with the correct coverage level is through the Bootstrap, and we have written software for doing this in both Python and R. So yeah, basically, we also prove in the paper that you get the correct coverage level. You know, if you're aiming for 95% coverage, or that's what you get. Okay, any questions before I go into the experiments we did on actual remote sensing data sets? All right, so we ran a bunch of experiments varying kind of the specification of the regression, as well as which variables are remotely sensed versus ground truth. So, and this was done in a paper led by my grad student, Carrie Liu. And so this one also is on arXiv if you'd like more details. So here we have 4 examples spanning things like doing a deforestation logistic regression where deforestation is the remotely sensed variable. So the response variable here is the Y variable, and then the covariates are the X's. In the first example, we are regressing deforestation on distance from roads, distance from rivers, elevation, and slope. Second regression is looking at tree cover, and it's a linear regression with aridity, elevation, and slope. Third example is one that you've already seen, looking at housing price regressed on income, night lights, and road length. And then night lights and road length are the 2 that are remotely sensed. And then lastly, we have forest cover regressed on elevation and population. And in this case, both the response variable and one of the covariates is remotely sensed. And then the red points, I'll just note, are where we have ground truth. And then here in the legend, you can see how many ground truth points we have. I think here I haven't written down how many map points we use, but it's at least 1 or 2, it's like usually at least 2 orders of magnitude larger. Okay, so this, these are showing the results of the regression coefficients that we get from each of those 4 examples. And we're comparing 3 methods. One is using only the map, using only ground truth data or GT, and then PPI, combining the map and the ground truth data. And then we're estimating an intercept term for each of the regressions, as well as coefficients on each of the covariates. There's 2 metrics that we look at here. One is what is the bias and the magnitude of the map only estimate. So of course, we've been talking a lot about how treating the map as if it were totally correct can give us biased estimates. In this case, we look empirically at what is the magnitude of that bias? How much of a problem is it? And then the second thing that we look at is compared to only using ground truth data, what was the effective sample size improvement that we got by combining the map with the ground truth data? So that's this like something X number that we have for each of the PPI confidence intervals. So we have actually a notion of what is the true coefficient for the last 2 regressions. And so I'll start there. Basically, you can see sometimes the map only coefficient, it turns out not to be biased. But sometimes, we saw a bias of, plus 64% or plus 47%. So in other regressions, I'm not showing here, we've seen even, I guess actually I have a simulation in the next slide, but these biases can also get, of course, even larger depending on the quality of the map product. And then the amount of sample size gain you get over using only ground truth, if you combine it with the map, it also ranges kind of depending on how high quality your map product is. It can be anywhere from being close to 1x, so not much gain, all the way to the best that we saw in our examples was a 17x sample size improvement. So you have basically for the income coefficient in this housing price regression, it's as if you had 17 times more data when combining, because you use the map in addition to ground truth. So you have a much more confident estimate of what the true coefficient is. And indeed, you also see that the PPI and the ground truth only confidence intervals intersect with a true coefficient, like every time we actually know what the true coefficient is. Okay, so the last experiment I'll talk about is we try to tease out what is the role of map error, or basically the error in the machine learning algorithm, by decomposing that into noise and bias. So we simulated noise. In this case, for this regression specification at the top, we added noise and bias to just the population covariate. So we just assume that we have, a proxy for population. And in the experiment where we simulate noise, we just add a Gaussian noise to it. We also add noise to the response variable y. So we have like a map, like a quote map version of y, where we also add Gaussian noise. This plot here is just showing, what that X map versus true X looks like, and what is the R squared of that regression. It's about 0.5, which is not super high, but also not unheard of. It's like actually quite common in a lot of remote sensing based maps to get this kind of R squared. And then for the bias experiment, we have a map version of X population that's like a square root of the true population. And this is our way to simulate if you have something like the yield mapping situation that I showed near the beginning, where basically the map's not able to capture low yields. Like its predictions just kind of saturate at the low end. So this is what we're trying to simulate with the square root function. And then there's a term C here that just interpolates between true X and this square root function. Okay, so when we inject noise into X and Y, this is what we see. So the results here, the panels are noise in X, noise in Y, noise in both. And then we're looking at the coefficient on elevation and the coefficient on population. So basically when you add noise to Y, the map only estimate, which is these like red points, they actually don't become unbiased, which is what we expect from the theory. But if you have noise in X, or in this case in X population, you see what we call attenuation bias, which is also what we expect from theory. Basically the true coefficient, which is this dashed black line around, 1.5. When you actually have more and more noise in X, if you treated the map as if it were totally accurate, you would get a coefficient, more than half, at the very extreme end of noise here, basically like 50% too small. Whereas the PPI estimate, it successfully accounts for the noise in your map product, and it's basically making the confidence intervals wider and wider, as it should, because it's expressing the true kind of uncertainty in what the coefficient is, because we know that the map product is getting less and less accurate. So rather than confidently predicting that the coefficient is actually 50% of what it actually is, PPI is telling you, your map's not very good. We can't actually distinguish the relationship between population and, in this case, I think housing price. Wait, I think this is tree cover. We can't distinguish that coefficient from 0. All right. When we add bias, what we see is actually the PPI confidence intervals, they don't get too much wider, unlike when we add all this noise. What we see in the map only estimator is that it really becomes quite biased. Especially if you have noise in both, bias in both, then it really veers off course, and you get an estimate that's 3 times larger than what it should be. Okay, so that's kind of the effective noise versus bias. I'll just maybe skip most of the slide, but the main requirement in order to use our method is to have some kind of random ground truth samples. And that's really also the main limitation, because a lot of applications may not have that. So if you don't have that, then you would look at one of the other methods, I think listed in the table previously, where you make some assumptions about prediction errors. You know, in the absence of data, you have to make some assumptions in order to correct for bias. So I would say the takeaway for map makers is to release your holdout set, aka your test set. And this is something, I mean, this is also true for, you know, people making machine learning, releasing the predictions from their machine learning model. In order to use a method like PPI, we need the ground truth samples in order to debias our map-based estimate. And, you know, without the map maker releasing a test set, then people who are doing the downstream analysis have to then generate their own ground truth data, or they're just not able to use that method. So it's currently not the norm in remote sensing when you make a map or when you release a map to also release the test set for the map. It's also not common to release, you know, an uncertainty layer in addition to the map itself. But I would really encourage people in the field, like if I had one message for our field, it would be to release your test set, because then you're enabling downstream research to estimate quantities that they're interested in an unbiased way. And that's really ultimately one of the main reasons that we make maps, is so that people can use them for analyses. And so that also broadens the impact of your map. Okay, I'll conclude there and take any more questions. Thanks.
Thank you, Sharon. Do we have questions? Yes, Leif has a question.
Yes, I have a question. So it seems you're using these fairly classical linear regression types. And I don't know if they're simplified here, but I didn't see any interaction terms, for instance. Is that not something you use at all, or is it because it's simplified in this presentation?
Oh, so a lot of the regressions that we show here are kind of just to illustrate the method. But I mean, in reality, you could do a linear regression and include a bunch of interaction terms. You can have quadratic terms, you can take logs. You know, people do all of these things, and that doesn't change.
Yeah.
the
Okay. Yeah, I understand.
Yeah. It would still be a regression.
Yeah. Got it. Thank you.
Yeah.
Alexis?
Yes, thank you for a great presentation. I was wondering, or maybe I missed it, but did you analyze the impact of the number of these ground truth points? Because I would assume that, you know, if you have very few versus many, maybe this was part of some of these here. Sorry.
Yeah, I didn't talk about it explicitly, but I think you can kind of see
So
it.
for example here, sorry, this plot, if you go back. Oh, sorry, this one. I mean, I guess the width of the green one, for example, might depend on the number of, or like the percentage of actual points in the.
Yeah. So definitely the width of the blue one depends on the number of ground truth points, and then the green one depends both on the number of ground truth points, but also on the quality of your map. So if you have very few ground truth points, but it turns out, you know, in the best case, your map happens to match ground truth perfectly, then the variance of this would be 0. But if you had, yeah, I mean, I think little n would play into this, but this part is a function both of little n, so how well you're able to estimate this thing here, and how good your map is.
Right, thanks. And then also another sort of question regarding your final takeaway there about you know, publicly releasing the test set. I guess one argument from the other side would be that if you do release test sets, there is a risk of sort of community overfitting to the test data, so that you know, if people can, I guess, isn't that one of the reasons why people hold out tests sometimes, because it sort of limits the amount of experiments that you do on the test set, which kind of makes it less likely to accidentally overfit to test, if that makes sense. Do you agree about that?
I think that I think the test set corresponds, like the test set would be a holdout set for a particular map. So if I'm a downstream researcher and I'm interested in using, you know, the Hansen, like Matthew Hansen's deforestation map, then I would need, in order to combine, or like to basically use the map, but also be guaranteed that my inference is unbiased, I would need a set of holdout points that Hansen and all did not use to train their deforestation map. So either I can generate that myself, or it would save me a lot of time if Hansen and all released a holdout set that they used to validate their map. So,
Yeah,
you know, if they release that data, of course, I think, you know, I'm sure other people would grab that data and then train, you know, new deforestation maps on it. In that case, you know, as a researcher doing the downstream analysis, I wouldn't be able to use that test set for someone else's map if they used it in their training set. But I would be able to use that test set for the map that Hansen et al. Made. So it's true. I guess it's like every map needs to have its own test set, right? Something that was held out of the training process for that map. But I can't guarantee that other people in the field won't just take that and use it in their training set, of course.
Yeah, I understand. Thank you very much.
Yeah.
The philosophy of generalization. So Chiara has a question.
Hi, sorry, I'm in a house full of people from kids mostly, and I arrived a little bit later to the talk, so maybe you already said that, but I still would like to ask. So you said that well, this analysis, which I think it's fantastic, by the way. I love to see this sort of estimation of errors and biases on also remote sensing data, which I feel that is very much missing. But anyways, so you talked about how good is your map, and I didn't really get in which way you established that. And then I have a follow-up question. So you said that you can do this sort of analysis when you have some quantity that is remote sensed. And do you mean also if it's something that you can derive, like let's say we take like Sentinel-2 data, so the multiple bands, and you can estimate like a quantity by doing some operation with multiple bands. So how does the error or the bias propagate through the single channel? So to say, have you looked into it?
Yeah, so we're talking about anything that is the product of, I mean, it doesn't even have to be remote sensing data, but nowadays, just any pipeline where you estimate a particular variable. And the most common way that people do that in kind of environmental applications is remote sensing data like Sentinel-2 fed into some machine learning algorithm, whether that's a random forest or a deep learning algorithm, to predict something like deforestation, tree cover. It could be many things, night lights, road length, etc. The nice thing about our method and the reason we took this approach is you don't need to know things about the error structure of your map, because you have ground data to tell you what's the bias that you get when you used the map to perform your estimation versus if you use the ground truth data. So, you know, right now people make remote sensing maps. They, you know, if it's a classification task, they'll do a confusion matrix and they'll report accuracy, F1 and all these metrics. But then they don't release their ground data. So it almost, for this analysis, it almost doesn't matter exactly what those metrics look like. You know, with the tuning matrix that I described, you know, you're guaranteed, if you combine your map with your ground truth points, to have a variance that's lower than the variance of if you just use your ground truth data by itself. And the role of ground truth data here is to give you this bias correction. And so again, it doesn't matter what form, what is the shape of the error. Like Like it doesn't matter, you can just estimate this bias correction and you're guaranteed that your beta hat PPI is unbiased and will converge to the true thing that you're trying to estimate. I hope that
Okay.
does that make
Yeah, I understand. Like I was just wondering if you could then, like if you like somehow retrieve also the error on the single channel, so to say, like then you could use the same correction, the same bias correction for other calculations later on. I mean, I'm thinking if you then will use this, like maybe that same channel for which you have the error for some other analysis that you already have information on the bias. But yeah, but I understand what you mean.
I will
And
say,
like,
yeah.
mm,
I will make one more comment, which is this kind of bias correction term, it will be different for every regression specification. So, you know, if you add a covariate,
yeah,
this can change, right? Will change.
yeah,
So
yeah, absolutely right.
you can reuse the ground data, but it's hard to kind of
Mm.
maybe reuse other things. Yeah.
Okay, thank you.
Yeah.
Great. So I think that will have to wrap up the discussion for today. Thank you very much, Sherry Wang, for this amazing talk.
Great.
Really inspiring stuff. In 2 weeks' time, we'll have the next talk related to environmental data. We'll listen to a talk about machine learning for Earth system prediction and predictability by Maria J. Molina from University of Maryland. And before that, we'll meet next week when we'll have Oriol Nieto from Adobe talking about generative AI for sound design. So thank you everybody for attending, and especially to Sherry for this talk.
Great. Thank you so much.